Welcome. This video will learn about gear ratios and will explain the concept of gear ratios and transmission of power between different gears of different radiuses by this example. So we have here these two shafts with two gears connecting them. The two gears will have two different radiuses and the right gear here will have an input torque. So kind of the power flows from the right gear, right shaft to the right gear, to the left gear, to the left shaft. So there is input torque, T1, and that input torque causes rotation of the input shaft in this direction. And when one gear moves in one direction, the other gears kind of connected to it and follows. So kind of your direction of rotation, if you're looking from the same side, of the gears switches. So if the right gear, if you look at it from the right, you will see it's rotating counterclockwise. But the gear connected to it, the smaller one, is now rotating clockwise. So the rotation switches between the gears connected to each other. And now that rotation will just, if we analyze now, because we're dealing with strength of materials and statics, so we're analyzing the tendency of that system to move, but it didn't move yet. So we're analyzing the equilibrium of it just before moving. But it's good to analyze equilibrium, especially in that type of system, movable one, in connection to it also the movement of the system. So I have the input torque, the top, the right shaft and gear wants to rotate counterclockwise, the other shaft connected to it and gear wants to rotate clockwise, and what prevents it from doing that rotation, clockwise rotation, the output shaft, is a reaction torque, which is the opposite way. So it's kind of interesting that we have to do that kind of right brain, left brain, kind of the right brain is the equilibrium, left brain is the movement. Because that will help us to clearly explain the gear ratio. So that can be one way, other textbooks show it in a different way, but I really personally like to differentiate between equilibrium of forces and torques and the movement and the connection between the different moving parts here. So now once we kind of make that distinction between torques and movement or rotations, now we can take out these two gear system and shafts, split them. So I have now the right input part of it and the left the output part of it, and we're trying to kind of analyze the relation and the interface and interaction between the tooth of each gear with each other. So what before movement, we're analyzing the equilibrium. What prevents the input shaft and gear from movement is a force F1. So if it tries to rotate this way, then there's something preventing it from rotation just before moving. And the same applies to the other gear. So that resistance moment or torque T2, it's being overcome by a force F2, countering it. So one thing here that these two forces, F1 and F2, are the interaction of the two gears. So they actually are equal forces. So it's kind of my right hand, or if you look at it, this hand and this hand. If I'm pushing and they are in equilibrium, I can take out this hand and put a force that says represented by just a force in opposite direction, right? So my arm is resisting a force from my hand on this hand, all right? So it's just an interaction force on two different bodies, and these two forces, F1 and F2, are equal. So now what's the relationship between each force and the torque? We have seen that in a previous video. A torque is equal to the force times the distance. So that's a torque is a moment, right? So force times distance. Then if we look at the first, the output shaft and gear, if I call the radius here R2, then T2 is equal to or in equilibrium with F2 at distance R2. And I can do the same for the input gear. So T1 is equal to F1 times R1. And if I know that F2 and F1 are equal, so F2 is equal to T2 over R2 and F1 is equal to T1 over R1. So this means that the output torque T2 is equal to T1, but now adjusted by this ratio between the radius values of the connected gears here. And this ratio between R2 and R1 is what we call the gear ratio. It's very important and very very intriguing concept. Seeing, and I will share with this video another video, a very cool animation of really the gear ratio in action and how you can magnify the torque from an input power, and the power here transmits, and pay attention that the power transmits we assume here without a loss. So the power is the same, it's just the way you transform the power from low torque to high torque and low speed, or from high torque, low speed to low torque and high speed. So it's very cool concept here. One thing that I just mentioned is that power is transmitted without loss. This is what we assume. So, and power, we learned before also that power is equal to 2 pi ft. So 2 pi the frequency t. So if you plug in P1 power 1 is equal to power 2, and you plug in T1, T2, and the relationship here, the ratio of the gear here between the radius values, you will find that you will end up with another formula for the frequency. So F2 is equal to F1, but now the ratio of the gears is flipped. So it's R1 over R2. So to summarize, if let's say R2 is less than R1, like in this case, the second gear is a little smaller than the first one. So if this happens, then the torque on the output torque here, T2, will be less than the input torque, but I will get higher frequencies. So the gear or the shaft, the output will rotate faster than the input. And if you want to see R1 or the other case, R1 is less than R2, it will be the flip story of that. So gear ratio is very important concept, especially if you are mechanical engineer. It's a very cool concept. It will help you to understand how power is transmitted and how it's actually one of the very ancient concepts, and how gears are helping us to overcome a lot of load and work conditions that are beyond our human capabilities. So that's it for this video, and I will see you later. Bye.